Okay, so the next aspect that I want to talk about is just the stress-strain relations. And our voice notation that we've now established, we can rewrite the strain vector as a 6x1 and the strain stress vector as a 6x1. So that is the sort of the most general three-dimensional version that we can have a representation for stress and strain relations. Okay, and in terms of symmetric stress tensors, because be cognizant stress tensors, as we'll see a bit later, doesn't always have to be symmetric, but in this course and in the necessity, they'll always be symmetric. Okay, so let us first start to understand this. What it implies is that we have sort of a 3x3 stress tensor and a 3x3 strain tensor. That is essentially what we try to relate to each other. Okay, so if I think about that just from a pure relationship kind of point of view, to relate that in the most general kind of linear mapping that I can build between those two things, of mapping from a 3x3 strain tensor to a 3x3 stress tensor, the most general mapping I can have is sort of a 3x3 by 3x3 matrix. Okay, so that is essentially that, because if I were to multiply this 3x3 and contract it, so if I take the strain tensor matrix, for instance, I contract it with two of those dimensions, so this 3x3 by 3x3, this sort of four-dimensional tensor, and I contract this dimension and I contract that dimension to that dimension, I end up with a 3x3 stress tensor. So this is why it's the most kind of linear mapping that we can have. And if you think about that, essentially, so a 3x3 is 9, times another 3 is 27, times another 3 is 81 independent components that we have. Okay, but luckily we know that because of symmetry, in this stress tensor, when we don't have sort of micro spins or micro moments in the material, and strain tensor symmetry, we be down to 36 independent components. That is essentially we're reducing some of those freedoms and saying we're not looking at the most arbitrary general mapping, but now we need to make sure we preserve at least the symmetries. Then we end up with something that's got 36 things that we have to know about that material relationship between the strain to stress. That's a lot of components to know something about. Okay, so then there's elastic, hyperelastic material. So I see. So that is essentially additional assumptions that one can make towards the material, and that brings us down to 21 independent components. We can have sort of single plane of material symmetry that brings us down to 13 independent components. So that is just a single plane where we have then symmetrical kind of behavior across. If we go down to sort of orthotropic materials, that's often referred to as 2/3 perpendicular symmetry, but that is sort of related to often to laminates and composite materials, orthotropic. So that's essentially comes down to 9 independent components. If I have one plane of isotropy, so a plane in which everything is isotropic, so in all directions in that plane things are the same, down to 5 independent components. And if I sort of have a complete isotropy, so infinite number of isotropic planes, I end up with 2 independent components. And that is the kind of world that we'll be living in. If I know 2 things about the material, I'll be able to relate stress to strain. So this is just by basing additional assumptions on that generalized mapping, we can end up with actually only having to know 2 things about the material to be able to describe what's going on there. Okay, so that is essentially what we're learning from this. And what these 2 materials are, as you know from material science, is typically Young's modulus or Poisson's ratio or bulk modulus or shear modulus, and they're all related to each other. So you can express it in different formats, but essentially, if I know 2 things about the material, I can map the strain field to the stress field. Okay, so the question is, how does this mapping typically look and work? And for that, I'm going to just maybe switch back to the light board. We can maybe just quickly draw this. Okay, so what we're going to be looking at is sort of what's called the generalized Hookean law. So it's generalized. This is quite a stock standard sort of derivation for this. So Hooke's law essentially that we're going to be generalizing. Okay, so oops, my pen is also now. Just make sure I get this. Okay. Okay, so essentially what we recall from 1D case in terms of Hooke's law is that stress is related to strain. So this is now sort of that 1D version of it. And how does this now generalize? So if this is now becomes sort of a vector and this becomes sort of a vector, what happens in this case? Okay, so for that again we can just make sure we leverage the linear superposition to really try and understand. So we could think about 3 cases of things that could happen essentially. So let's look at that first. So I'm going to be talking now essentially relating strains in the XX direction. Let's look at how things can strain in the X direction. What are things that could contribute towards that? So let's first off draw sort of examples of that. So I could have sort of a cube. And so let's just give down a coordinate system here, X, Y, and Z. So we just have that control. And if I were to apply sort of a loading in this direction to this cube, then this cube would essentially this is sort of what would happen to that. Very exaggerated. Oops. What am I doing here? Okay, so very exaggerated what's going on there. But that's essentially what we see is things would sort of stretch and there would be the Poisson's effects that would cause some contractions. Okay. And so this amount of stretch that we would have there is essentially saying, okay, if I know from the Hookean law that stress and strain is related this way, let's then isolate strain out of this and say, okay, strain is essentially just the stress that we've applied in the X to X direction in this case now. So let's just call it stress over epsilon, and we can now keep track of the directions, whether it's XX or YY for ourselves. Okay, so if I've applied here sigma XX, then essentially what I see is that contribution of the strain would be there. So let's write that contribution down. So that is essentially sigma XX divided by Young's modulus. That is what I have. I might have another loading condition in that same kind of structure at the same time. And from superposition, I could say, let's start off with this cube. And I might have applied a loading in the Y direction, sigma YY, loading to this structure. So the thing might have okay. So that sort of looks like that. Ooh, let's draw it a little bit better. So this is terrible. So let's draw that axis first. Okay, let me just wipe this off. This is not good work of art. Okay, so that is essentially what could have happened there. And if I ask myself now, okay, so I'm not interested in what's going on the strain in the Y direction. I'm interested in what's going on in the strain in the X direction. And what I'm seeing is there's a Poisson's contraction. So if I've got a positive, if I put this thing in tension, I would get sort of a strain in the negative that's sort of trying to contract in the X direction. So that contribution I could add in and say, okay, so there's a contribution here that is related to the sigma stress, but it's in the opposite direction too. If this is positive, this is a contraction in the XX direction over the material, but it's not the full amount, it's really that Poisson's effect. So it's related to that Poisson's contraction part. Okay. And so just a reminder, all of you, I should be very familiar with what Poisson's ratio is, but it's just if I apply a loading in one direction, it's how much I contract in the other directions. Okay. And so typically Poisson's ratios of materials can vary from -1 to 0.5. Physical materials typically from 0 to 0.5. Giving you an idea, if you're sitting with sort of a rubber incompressible material, then you're sitting with a Poisson's ratio of 0.5. If we sit with something that that people use to seal wine bottles with, like cork, essentially when you press that cork in, you don't see that cork popping in the transversal direction. When you compress that cork in, it doesn't become longer or anything. So that is, cork is close to a material with a Poisson's ratio of 0, where this contribution would sort of be falling away. Materials that have a negative Poisson's ratio, what that implies is if I pull on something, I don't contract, but I actually expand. And so those materials are typically mechanisms that get built, so-called nanomaterials. You can build a nanomaterial where you can design sort of a structure in it that if you pull it, it pops out. It's almost, you get those kids' toys that work the same way. But if you scale that down towards a nano version, you can make a material with that behavior where you pull on it and then boom, it actually expands. Okay. So that is a contribution of, so this is just to make sure that we're comfortable with the Poisson's ratio. Okay. And here we can see now, this is the two materials that I need to know about this is the two things that I need to know about material. This is one version of a description of two things I need to know about material to map strain to stress. And then there's obviously the third case, which is essentially if I were to now go in the z direction, and if in the z direction I'm applying now a sigma zz, for instance, then things might want to essentially also contract in that x direction. So that might be related to a sort of a stretching or a tensor compressive kind of mode in the z direction. But again, if it's positive, if it's tensile, then I want to see a contraction in the x. So that's going to be another negative of sigma zz over E. And I can follow exactly the same argument now to say, but what happens with epsilon yy? Well, exactly the same argument would hold. The contractions, if I pull in x and I'm asking now what's happening in the y direction, that's a Poisson's contraction there, so that would be then the Poisson sigma xx over E, and then it would be just as normal in the y. For the y, it would just be a tensile version. So if I'm looking at what's happening in the strain in the y direction, and then essentially same for the z would be sort of a Poisson's contraction. And I can do the same for the epsilon zz. Okay, so that is essentially what we have. So this now relates normals to shears. And what people have done in terms of materials typically, for the normal strains to normal stresses, this is essentially what this boils down to. And what people have done is essentially to try and relate shear stresses to say, well, how is it proportional to shear strains? Well, essentially what they've uncovered is that it's related by the shear modulus. So people have done experiments by essentially shearing material, measuring the angle, and seeing what was the sort of the loading that was required to get that, what was the stress state, and then be able to relate it and say, oh, that's related to the shear modulus. So essentially, if I want to write that, gamma xy is then related to the shear modulus by over G. Okay, so that is essentially what that relates to. And I can write this all now in a nice matrix form. And for that, I'm going to go back to sort of the slides. And if I go back to the slides and I look at this now in a more matrix form. So this is now just all of these equations that's written out nicely. There's the shears that we have. It's quite easy to relate the shears strains to the shear modulus to the Young's modulus. By looking at sort of an example where you pulling in the one direction, change the coordinate system, and then you can start looking at how would the shear behavior have looked, or if it was shear in the one direction, change of coordinate system, looking at how things are going in tensile, and then that allows you to relate the shear modulus to the Young's modulus. Okay, but that's not important for this course. The important thing is that we get towards a place where we can relate shear strains to shear stresses, and so that we get comfortable with that. Okay. So if I go and I take these equations that I've got and I just pull out the sigma xx, sigma y, sigma zz, and I write it in the matrix vector form, I end up with this relationship. And this is not always convenient, as you see now, because typically what we started off with, we had now the displacement field, we were differentiating that, we got to the strains, and now we want to be able to get to the stresses. So we can then sort of symbolically invert this, and then and that you can really do with SimPy very easily to just invert this expression, and then you end up with this sort of relationship to say the strains are related to the stresses, and this is the relationship that we have. Okay, and you can see essentially what is the role of Poisson's ratio and the role of Young's modulus in this. And this is the generalized Hookean law. So this is now relating in a generalized way, in a three-dimensional way, taking the one-dimensional kind of idea, using linear superposition, and ending up in a place where we now beautifully relate strains to stresses. Okay, so that concludes sort of this part of how do we relate now strains to stresses in a nice systematic way. And what's now left is essentially to say, okay, so now that we have the stress fields, so what this allows us to do, if you think about it, we can now go from displacement field compute the deformation gradient. From the deformation gradient, compute the strains, tensor, reshape it into a Voigt notation, use generalized Hookean kind of material constitutive laws, map the strains to stresses, and now I've got a stress field. The only thing that now left is to ask ourselves, but is that stress field, when is it in equilibrium? When is it a legitimate stress field and when is it not? And so the concepts that we can explore then are additionally, what is this stress field? When is it in equilibrium? What are the conditions that need to hold so that we can at least check that? And then the other aspect is if I apply loadings to a structure, how does those loadings relate to sort of stressing the stress in that structure? So these loadings are typically called surface tractions, and what is their relationship back to the strain, to the stress in that structure? Okay, so that is what's going to come next.